Hello everyone. In this video, we are discussing the solution to the last problem from INMO 2024. So it says that an equal to square root of n plus 1 plus till square root of n square plus 2n minus 1. And similarly, we define bn from n square plus 2 till n square plus 2n. And we need to figure out for which positive integers can we conclude that greatest integer of an equal to greatest integer of bn. So this we need to find for which integer these two numbers are equal. I think the solution to this problem is slightly like it is motivated from a result in calculus, or basically you can say that if you know calculus, it will be slightly easier to solve this problem. So I will be using calculus in my solution, but there are alternate solution to each of my proofs. So first part is let's figure out what is the value of bn minus an. So bn minus an equal to square root of n square plus 2 minus square root of n square plus 1, and in this manner we can pair up the terms from square root of till square root of n square plus 2n plus square root of n square plus 2n minus 1. And if you use rationalization, if you do rationalization, you can conclude that this is equal to plus square root of n square plus 1 plus and so on, and there will be a total of n terms. These are n terms. And note that square root of n square plus say here we are writing n square plus k plus n square plus k plus 1. These are two numbers, and of course this is greater than 2n. Why is this? Because square root of n square plus k is greater than, let's say, square root of n square plus square root of n square, which is equal to 2n. And so what you can do is 1 by 2n is greater than 1 upon square root of n square plus k plus square root of n square plus k minus 1 k plus 1. And if you do this for all the terms above, you can conclude that this whole big term here, let's copy it. Yeah, so this big term here, this is less than 1 by 2n into n, because there are a total of n terms, which is equal to half. So this is what we conclude. So our first result is bn minus an is less than 1 by 2. This is our first result. Now let's try to figure out something about bn plus an. So bn plus an, which is equal to square root of n square plus 1 till square root of n square plus 2n. So now we will use some inequalities from integrals. So what you can do is you can say that square root x dx, integral of square root x dx from a to a plus 1, this is of course greater than square root of a. And similarly you can say that square root of x dx from a to a plus 1 is less than square root of a plus 1. These are two very important results. So using that, what you can say is, let's take an expression bn plus an plus n plus 1. So this is equal to square root of n square plus 1 plus square root of n square plus 2 till you can go till square root of n square plus 2n, and the last term here, which is n plus 1, will become square root of n square plus 2n plus 1 plus square root of n square plus 2n plus 1. And what you can do is you can write that this is greater than square root of a square to a square plus 1 square root of x plus a square plus 1 to a square plus 2 and square root of x, and so on till you can go till a plus 1 square minus 1 till a plus 1 square square root of x dx. And this basically becomes equal to integral from a square to a square a plus 1 square, square root of x dx. And if you evaluate this integral, this is basically equal to 2 by 3 x to the power 3 by 2, and the limits are a square to a plus 1 square, and this basically evaluates to 2a square plus 2a plus 2 by 3. This is what you get. So you conclude that bn plus an, wait, yeah, so here I replaced, these are basically n's, I replaced them by a by, so this will basically become 2n square plus 2n plus 2 by 3, and thus you can conclude that an plus bn is greater than n square 2n square plus n minus 1 by 3 by subtracting n plus 1 from both sides. This is one inequality which we get. And the second inequality, by doing a similar expression but opposing the inequalities, you can get that an plus bn is less than 2n square plus n plus 2 by 3. How do you get this? You can get this by observing that, like, uh, in the earlier expression we used that square root of x dx from a to a plus 1 uh, is greater than square root of a. This we use, but if you reverse this as this thing, then you can get the second part. Okay, so these are the two inequalities which you will get. So from this, what you can do is you can conclude that the greatest integer part of an plus bn, this is basically equal to 2n square plus n. So this is what you get. Sorry, yeah. So what you can notice here is that we are getting two inequalities here. Okay, so from these two inequalities, after getting these two bounds, let's try to analyze what we have, what is the current situation. So basically we know that an plus bn is equal to greatest integer an plus greatest integer bn plus their fractional parts, and we know that this is greater than 2n square plus n minus 1 by 3, and also we know that these two fractional part combined are less than 2. So this means that if square root of an equal, if greatest integer an equal to greatest integer bn, we can replace this by 2 times greatest integer an, and we know that this is greater than 2n square plus n minus 7 by 3. And further, what we can do is we can convert this 7 by 3 to 2 by putting a greater than equal to sign and noting that the greatest integer n is an integer. So this becomes 2n square plus n minus 2. So this means that greatest integer an should be equal to uh, a n square plus is greater than equal to n square plus n minus 1 by n square plus n by 2 minus 1. Okay, so this is what we got till now. And but looking at this expression, the most obvious value of square root of an, sorry, greatest integer an, seems to be n square plus n by 2. So let's try to see what kinds of bounds we get from this number. So what we can do, let's consider the number an minus n square minus n by 2. So this basically becomes square root of n square plus 1 plus n square plus 2n minus 1 minus n square minus n by 2. So what we can do is we try to uniformly distribute our remainder. We consider these numbers of these form and so on. So what this becomes is we will notice some inequalities, n square plus 1 minus n, and this is basically 1 upon square root of n square plus 1 plus n, and notice that this is less than 1 upon 2n. Okay, so 1 upon 2n, and using a chain of similar inequalities, we get 3 upon 2n till we go till 2n minus 1 upon 2n. Okay, and adding all of them up, we can get that an minus n square. This is basically less than 1 plus 3 plus 2n minus 1 upon 2n, and this is basically n square upon 2n, and this is 1 by 2, sorry, n by 2. So this means that an is less than n square plus n by 2. So this is the inequality we have. And performing a similar calculation on bn, we can get that bn is greater than n square plus n by 2. So this makes it clear that greatest integer an cannot be equal to n square plus n by 2. Okay, so the only choice we have is greatest integer of an has to be n square plus n minus 1 by 2. This is obtained by combining with this inequality. And after that, if greatest integer of an equal to n square plus n minus 1 by 2, then using the fact that bn minus an is less than half, you can conclude that greatest integer of bn will also become n square plus n minus 1 by 2. Okay, this is obtained with conjunction to this inequality, this set of inequalities. Work out a little bit. I am leaving it as a homework. So after that, what you can do is notice that when does n square, notice the fact that bn is greater than n square plus n by 2. So if n is even, then greatest integer of bn becomes n square plus n by 2. This is because bn minus an is less than half. Okay, so this means that n has to be odd. N has to be odd. And if you check carefully all the given inequalities we have derived so far, you can conclude that whenever n is odd, this condition is satisfied. So square root of an equal to square root of bn if n is odd. And notice their common value, square root of an becomes equal to square root of bn, and their combined value is n square plus n minus 1 by 2. So this is the answer to our problem. Thanks.